Okay, so got some problem for the projector and already fixed. So good afternoon, everyone. I'm Edmund from Intel Software Architecture. So today's presentation is for how to use system power telemetry into the data center facility management. So this work is based on our collaboration with cloud customers. By the way, the first author for today's presentation is Nishi Ahuja. Nishi is Intel senior principal engineer, but she's in international travel and not available for today's presentation. So that's the reason I'm standing here to present today's session on behalf of Nishi. So today's agenda will have three parts. The first part is the background, why we are caring about the facility efficiency, and why we are trying to connect the system telemetry or power telemetry into the cooling facility system. For second agenda, I'm going to discuss some learns and challenge where we are trying to integrate the system power telemetry into the cooling facility. For the third part, I'm going to talk about some details for how to use the power prediction technology into the cooling facility efficiency. So let us look at the background. So why we are so caring about the data centers facility. So look at this chart. So if we are still at 2010 energy efficiency, at 2020, the annual electricity use will be huge. This is a pretty steep curve. And people spend a lot of effort to improve data centers efficiency in past years. Transforming to hyper data center. The hyper data center technology is one architecture based on the software-defined and commodity-based hardware to support the large-scale deployment. It can provide much higher resource utilization and lower and higher energy costs compared to the traditional data center. Improve the management at a large scale. We can use the data center to monitor the power, temperature, and resource usage. And based on this monitoring, we can determine the underutilized resource, like the server resource, like the rack power capacity. Connect to IT to the facility management. With this connection, we are able to adjust the facility capacity according to the IT equipment demand. So they are also best practice to help improve the overall efficiency. Expanded the environmental range to the hyper temperature operations. Free air cooling. Use the natural air of water to cool down the data center's temperature. So use the liquid cooling or immersion cooling. Custom the rack and server design to put more compute with the same footprint, improve the power delivery system's efficiency. So this method can help us to improve the data center's efficiency and make sure the annual electricity use is kept flat. So I believe a lot of people are familiar with this picture. Yes, this picture is from Google's paper. Google tried to use the DeepMind artificial intelligence to help them to reduce the data center cooling bill by 40% and the PUE reduction by 15%. So this is a huge number. How do you get this? So this is the logic behind. They use 1,000 sensors to collect the data from the historical data from the data center. The data includes the power, thermal, and some facility sensors data, and use the neural network framework to learn this data and to use this data to train their control system. This helps them to approach this goal. Okay, this pie shows the overall TCO structure for the hyperscale data center. So we can see the power and cooling cost account for 30% of overall TCO structure. So the goal for our optimization is clear. So we should lower down the power and cooling cost. We should improve the or put more compute, put more workload to get more performance return with the same power and cooling investment. So let me move to the next agenda. So in this part, I'm going to discuss some learns and challenge where we integrate the power telemetry into the cooling facility management. So the telemetry and automatic is our approach to the automated data center. This is a circular process with 4 steps. The first step is watch, to expose the infrastructure attribute to the data center management. So we will focus on how to get out the data and what kind of data to be get out at this step. The second step is the decide. So around the data we have collected from the first step, what kind of sense behind this data? Is the data for the power efficiency or cooling efficiency? Is the data for the resource utilization, or that data for the performance per workload or performance per rack? So based on this data analysis, we can decide the control policy for next step. So the third step is action. So based on the sense we learned from the data, so we need to define how to control the loop to make sure we get more efficient data center. We get more automated data center. The last step is learn. Over the time, we keep learning the data and to use the data to build the intelligent model to be adaptive to the changing data center workload. Everyone knows our data centers workload deployment is kept changing, kept evolution. So the infrastructure telemetry-based analytic is the foundation to develop the trust and to raise the data center IQ, intelligence quotient. So this diagram shows our case for how to put the system power telemetry into the cooling facility management. So the whole process like this. The data center management collects the power telemetry from a bunch of servers, including the system power, component power. We can also use the data center management to collect the power from the power system, like the rack PDU, like the power cabinet. So when the data center management collects this data, it will do the data analysis. So to learn the power variation trend, is the trend going up or is the trend going down? Or what's the slope for the power variation trend? Then the power prediction algorithm is able to predict the power consumption within 5 or 10 minutes. Anyway, the prediction granularity here is minute level granularity because we are going to use this prediction for the cooling. We don't need a too fast prediction window. And based on this prediction, we are able to transfer this prediction data to the cooling facility controller. Then the cooling facility controller can manage the cooling capacity for the prediction window. So we can see for this whole process, we include the watch, decide, act, and learn. And also we have 2 kinds of interface. One interface is between the data center management to the IT equipment, between the data center management to the power and the cooling facility system. So the data center management needs the telemetry API to collect data from all these devices. Another side API is the control API. When the data center management to calculate to decide the control policy, it needed to transfer this control policy to the facility. Here is for the cooling facility. So here, this picture lists some basic, some fundamental ingredients or components within the data center. So we can see we have the IT equipment, server, storage, or switch. We also have the cooling system, power system, and data center management. So it's Much challenge for this component to talk to each other because a lot of different protocols behind this device. As we know, the cooling facility is using the Modbus or some other local bus technology. The power system is using the SMP, PM bus, or IPMI. Even some modern PDU are moving to the RESTful-based API. And for the IT equipment, the sense is much better because more standard protocol are used there. Like the IPMI is widely adopted by the server for power and thermal or some environmental sensor collection. And today, most of those IT equipment are moving to the Redfish. So actually, this diagram is borrowed from the Redfish power and cooling facility management spec. So the Redfish is trying to establish one common resource model and common resource API to support, to make sure the power and cooling facility at the data center wide can talk to the power and cooling unit in the IT equipment. So we are seeing the opportunity to use Redfish to build one common resource model and API to support or to ease the integration effort across the power thermal facilities, data, and the IT equipment and the data center management. So this common language can help us to reduce the complexity and cost for the solution deployment. So let's move to the third agenda, how to use the power prediction algorithm to help on the cooling efficiency improvement. So this is a typical data center cooling management system. And to ensure the safe operations of the data centers, the data rooms are equipped with a computer room air conditioning unit that use a traditional air cooling method. The servers mount in the racks on the raised floor, and the racks are arranged in alternating cold and hot airs, with the server inlet facing the cold air and the server outlet creating the hot airs. And the CRAC units provide the airflow in a certain temperature and airflow rate to the data center through the floor planium. The majority of the data centers in the world are using this method. So to develop one proactive cooling mode, the heat variation trend predictor is required to predict the heat variation at time t. And by adding the predictor into the cooling control loop, we are transforming the reactive cooling mode to the proactive cooling mode. In reactive cooling mode, the data center management collects the thermal information at the data center, and the CRAC unit uses this thermal information to control the cooling capacity. And for the proactive model, by adding the power predictor, the CRAC unit is able to use the observed thermal information at time t and the predict heat variation at t plus delta t. This is a prediction window to drive the cooling capacity within the next prediction window to better match the IT equipment cooling demand. So look at the right side of this page. The red line is the overall power consumption, and the orange line is the demand of the cooling capacity. So we can see that from the power usage prediction, the change in the cooling demand can be estimated by the power trend prediction. And the solid blue line is the supplied cooling capacity by the reactive model. And the dashed blue line is the supplied cooling capacity by the proactive model. So the result is an early response in supplying the cooling capability to meet the cooling demand. So how to do the evaluation for this case? So we develop one simple evaluation model to evaluate the result for using the power predictor into the cooling facility efficiency. So still look at the upper right diagram. The X is the timeline. The Y is the return temperature of airflow. We call it T return here. So along the T return will change along the temperature of the setting point. So we got overshoot area and undershoot area. So for overshoot area, we have the overheat risk. So we have the risk to overheat our computing components. And for undershoot area, actually we are over-provisioning the cooling capacity. That brings the waste of the cooling capacity. So still look at, so the cooling risk indicator is defined here to evaluate the overshoot risk. It's the definition for it is the integral calculus of the overshoot area. And look at the bottom right diagram. We have one line is the blue line. The blue line is the T return curve, the return temperature of the airflow. The T return curve without the power prediction. And the other three lines are T return curves with the different prediction window. We can see by adding the power prediction into the control loop, we are able to reduce the overshoot area. But what's the connection to the cooling efficiency? So still look at the left side of this diagram. And we can see there one red line, so over-provision line, I define that as. So generally, we need to over-provision the cooling capacity to avoid the overshoot risk. And by reducing the overshoot area, we are able to reduce the over-provisioning area. This helps us to improve the cooling efficiency. Okay, let us move to the call to action. So the IT platform telemetry intelligence are very important to drive the data center facility optimization for overall PoE efficiency. We need more value-added solution and more value-added design case for how to use the IT system telemetry in data center facility management. Because today we have so many sensors to keep the tracking for IT equipment for data centers. We should be able to use this data to help us on the efficiency improvement. So we are seeing the big challenge for the data center-wide interoperability, like especially for how to integrate the IT equipment telemetry into the facility management. So we need industry collaboration to define the common telemetry requirement spec and API model based on OCP community to support such case deployment. So let's be part of the hybrid evolution of the data center. Get involved into the OCP data center facility project with this link. So this is my today's presentation. Thank you.
So how many features do you have to use? How many features for training the model? You just mentioned the 3 features, power and temperature. I think there are probably many features.
For this page, right? For this page.
For the train the model.
So here, I think it's only for the prediction. It's still based on the power data. Okay. Yeah, we use power telemetry, the history of power telemetry, to just do an estimate for the short-term window prediction trend, the trend for the power variation.
Can you give me some details
like the system power, component power, and some power data from the power system, like the rack PDU and the power cabinet.
Okay.
Yeah.
Like the
Yeah. That's only based on the power prediction.
Okay.
Yeah.
So how often do you generate the model?
How often?
Like one day generate one time, or one month just generate the model for one.
So actually, in our test, we just build the model based on static historical data. But in real deployment, I suppose we have opportunity to fine-tune the model with more data input, right? Yeah.
So that means just generate the model for one time and keep using it.
That's right, because there is one assumption for the real deployment case is based on some internal cloud service, and the power consumption for that case is pretty stable. So yeah. But I believe, yeah, go ahead. Yeah.
Is there any thought to, because the word prediction,
Mm-hmm.
is there any thought to kind of bring in the workloads which drive the power consumption?
Sorry, can you repeat your?
Using the workloads?
Yeah, I believe we can use the workload, but for this case, for this collaboration, we just make sense to be simple for the real deployment. Yeah. Definitely, we can use the workload to base the workload to do more prediction, to do the refine, right? Yeah, definitely. But one challenge is, the workload, it's changed very frequently. And here, we are using this prediction for the cooling facility management. We don't need a so quick change curve for the cooling facility, because it's very slow to get the data center's cool temperature low down or up, right? So the prediction window for this case is 5 minutes and 10 minutes and 15 minutes. We use 3, yeah.
So how many data sets for getting the model? I mean, the data sets maybe you need like 1 terabyte or 10 gigabytes to generate the model?
I don't think it's measured by the data set. It's more like how long data we collect to generate this model. This case, we work together with cloud customer, one of our top CSP, to collect half year's data to analyze the power trend for each rack. This prediction is based on the rack, and then we summarize this overall power consumption to drive the cooling facility at the data center level. Yeah. Okay.
Power trending would give you a good opportunity to save energy in a data center that has a lot of variation in the loads. Many large data centers operate a pretty stable load, but one opportunity is there to save energy in that kind of a data center.
Yes. Yeah.
Okay, there's less opportunity. What about weather prediction? Do you have any kind of weather predictive analytics in your system here to?
Weather, you are saying the climate?
Yes.
Okay. So we think that's a good question, but I never imagined this. But I suppose that will based on if you are the free air cooling technology, right? So if you are free air cooling technology, we need to consider the impact from the climate change, right? But in this case, the assumption is still focused on the early phase. It's controlled by the, it's no impact. We didn't consider impact from the climate side so far, yeah.
Well, even with the chilled water plant or with indirect evaporative cooling or any large cooling, HVAC cooling system, the outside weather conditions will affect the performance of the cooling. There's an opportunity there regardless of the type of cooling system you use. Direct evaporative cooling, direct cooling like you're talking about would offer the biggest.
Yes, yeah. So okay, so if no questions, so let's close today. Any